All right. Good morning, everybody. I actually saw snow this morning. First snow this winter. It didn't last very long, and it didn't stick to my yard. But yeah, actual snow. I saw fall this morning. Okay. So last time we were talking about machine language and assembly language, and we wrote some example programs, and like till two such programs. So in thinking about this, we saw in a machine language program, it's ultimately about reading numbers from memory, putting numbers in memory, doing math on them, and jumping. And that was pretty much everything. I mentioned in passing that I/O is all a matter of interacting with the correct memory locations. So to kick things off this morning, what I'm going to do is talk about what's known as a memory map. That is, thinking in terms of machine language, all of the memory locations in the computer can be thought of as being mapped out with certain zones of responsibility. And by thinking in these terms, it becomes easier to think about how do I get the program to do what I want in terms of I/O. So the way that this memory map is organized is going to bring to mind much of what we discussed in the context of building the RAM chips, right? So specifically, when we built our RAM chips, the ultimate goal was this RAM 16K. So this 16K block of memory on a chip, and you all painstakingly put it together in a way that's traceable all the way back down to the NAND gate. So what this implies is that we've got this first region of memory, which is simply RAM. That starts at memory location 0 and continues to memory location 16,383. Why do I know that? 2 to the 14th power is 16,384. And then we start counting at 0. So all of this is just RAM. It's just places to put things. Thinking from this machine language point of view, it's sufficient. Later on, as we begin to develop more of an infrastructure that intermediates between a high-level language and RAM, we're going to be doing a lot to organize this region in a lot more detail. For now, though, we can just think of it as RAM. You might remember from last time in our discussion of generating a label that whenever you just make up a label, for whatever reason, it starts it at memory location 16. That is 0 through 15 wind up being reserved for a number of highly specific features early on. And it winds up being convenient to start arbitrary user memory at location 16. So here's the thing. The RAM available does not exhaust the totality of the address space. There's more to it. And when I say there's more to it, what I'm emphasizing is that you can actually store a value at 16,384 if you're so inclined. and it'll do something. It's not RAM as such, but it'll actually have an effect. More precisely, from 16,384 to 24,575, this is going to be the screen memory. This is going to be the screen memory. So what is it? How is it laid out? What's it all mean? So to think about the issue of screen memory requires thinking about the properties of the screen itself that the hardware makes available. For this particular simulated machine, what we're going to envision is a screen where each pixel is either black or white. Now, on conventional modern computers, right, this doesn't really hold. Specifically, what we have is that each pixel can actually be any of an extremely large number of distinct colors. What do we mean by extremely large number? Try that. So yeah, I think I'm hearing you all agree that that looks extremely large. So why 2 to the 24? There are a few reasons for it. There's red, green, and blue channels. They're each 8 bits. But this is how we've been doing color for a long time, and technology has improved, and why haven't we gone to a higher resolution? And the answer is we're beyond the number of distinct colors that the human visual system can actually distinguish, right? So given that, there's no need to be aggressive about figuring out, well, 24-bit color. Deep down, we know we can do better. How about 64-bit color? Can we do that technologically? Sure. Is there a purpose? No. Why? Because we're human and we have limitations. Yeah, right. In principle, you could imagine some unbelievably fine-grained distinction between varieties of some color that's intermediate between cyan and purple, but there's just no point. So 24-bit it is. Nevertheless, whether you've got 1-bit color, which is what we're going to be using, or 24-bit color, the underlying memory mapped idea is the same. Namely, you put a value at a memory location, and that value controls what pixel appears on the screen. Now, in this case, because each pixel only needs 1 bit, each of these memory locations is going to correspond to 16 distinct pixels. 16 distinct pixels. So this is all pretty abstract. Let's write a little code to exploit this idea. So, oops, there we go. I have maybe a few too many windows open. So it goes. So we're going to create a new program, a new assembly language program. Okay. And so what we're going to do in this program is just make a dash appear somewhere on the screen. Okay. So first line is going to be at, we want to fill in the 16 bits. Here we go. Actually, we'll do it like this. We'll say D equals 0, and then D equals, oops, D equals not D. In other words, we can fill D with ones by filling it with zeros and then doing the not operation. So our data register is now filled with ones. So now we're going to set up the address register so that we can store the ones somewhere in screen memory. So I'm going to set my address register to be 20,000. Why 20,000? It should be somewhere vaguely in the middle of the screen. And then I will say M equals D. And so that should store those values there. Of course, now that I think about it, we can make this even shorter. Say M equals 0 and M equals not M. There we go. So 3 lines. Nice 3-line program. Okay. So I'm going to go ahead and save this. And now we're going to try it out. So here is the CPU emulator. And this region over here is the screen display for our simulated computer. Okay. So we're going to walk through the program and watch what it does. So first, we put a 20,000 in A. Next, we're going to zero out that region of memory, which does nothing visible. But then when we negate it, aha, we have a dash. Right around there. I hope you can see it. So this is pretty momentous, right? We have now done output. It's kind of a big deal. This is putting us in a new kind of territory. Until now, our machine language was strictly about, just moving numbers around and doing math. And we can still do all those things, but now we've got a way of communicating to the user the result of having done so, which means that our programs can now have a purpose or a point. Pretty big deal. Any questions so far? We're going to play around with the number a little bit that we store in memory so we can get a feel for the layout of these pixels. So what I had done was I just filled the thing with ones. But there are other things we can do, right? So we're going to leave this beautiful example alone. We'll start a new program. So let's say we want the low order 8 bits to be filled. The low order 8 bits, so bits 0 through 7. To do that, we would store a value of 255 into it. Where do I get 255? It's 128 plus 64, which is 192, plus 32, which gets us 224, plus 16, which gets us to 240, plus 8, which gets us to 248, plus 4, which gets us to 252, plus 2, which gets us to 254, plus 1, which gets us to 255. So in other words, for each of those place value positions, I just add those values up, I get 255. Does that all make sense? I kind of did it all without writing anything. So forgive me for that. Okay. So now I'm going to need to use the D register. So specifically what I'm going to do is I'm going to load a 255 into the A register because that's the only way I can put a non-zero or 1 constant. And I'll say D equals A. And then I can say at 20,000, M equals D. So what I've done is I've told M, get the value from D, 255, stash it at that 2,000. We'll call this ASM4.asm. Okay. So now I'm going to go back to my emulator. I'm going to load, no, not a script, just need my program. Load my program. Notice it conveniently wiped out the screen for me when I loaded the new program. So now I'm going to walk through it. So A gets a 255. That gets copied into D. I set A to point at 20,000. M equals D. And notice that I still have a dash, but it's kind of smaller, right? It's kind of cut in half. But this is really useful, right? Because we can see, based on where those pixels are, that it looks like a row starts with the lowest order bit. And as you move leftward in the bit string, you actually move rightward on the screen. So that's how that works. And that's good to know. Any questions so far? Yeah, Andrew.
I have one just about the CPU emulator.
Yeah.
Whenever you load up your ASM
Yeah.
file, how do you, like whenever I loaded up my ASM file, it yelled at me for it not being in binary, and I had to use like something else to like translate into binary.
Huh. I didn't just load it for you?
No.
How rude.
Yeah.
That is odd. Well, I'll talk maybe about what it's looking for. ASM files should be assembly language. The binary files are .hack. The assembler program can translate your ASM into a hack file. And so that'll take your nice high-level assembly language and turn it into the ones and zeros. But yeah, it really should be loading without complaint the ASMs directly. When I use it, it's perfectly happy to just assemble it in place. So like binary, bam, there it is. That's odd. Maybe we'll take a look at it briefly after class, if you got your computer handy. Okay, we can look at it sometime tomorrow maybe, or this afternoon if you want to come by. All right, so there we are. There's the dash. Any other questions thus far? Yeah, Andre.
When you did the m equals not m, why did it change from 0 to -1 in the RAM?
Oh, great question. So it comes back around to the two's complement understanding of what these values are. So if, let me go back to the screen. We'll do a brief refresh on that. So in two's complement, remember, say I've got the number 1, and I want to find -1. So I flip all the bits, and I add 1. And so then I get all 1s. And so this is a meaningful -1 because if I go back and I add it to 1, I get 1 plus -1 is 0. So all 1s, no matter how many binary digits we have, will always be the representation for -1. And so when we saw it as a -1 in RAM, as you pointed out, that's because it was just interpreting those bits as a base 10 two's complement number. Yeah, so that's what was going on there. Great question. Great question. Other questions thus far? There are some programming languages that don't have a built-in Boolean type, and what they'll typically do is have constants where false is 0 and true is -1. And the reason they go with -1 for true is that if you do a not on all zeros, what you get is -1. And so every now and then you might imagine a situation where you're thinking about, well, what integer values do we use to represent them? Inevitably, true is -1. So useful to know. All right, cool. Where was I? Oh yeah, emulator. Cool. Any other questions so far about this little program? So at this point then, I think we're ready to read the keyboard and understand how input happens. Once we've done that, we'll ultimately put together a program that does both input and output. So you'll never appreciate a print statement or an input statement quite this much again. All right, so let's create a new program. Well, first, let's go back to our notion of the memory map. So in the memory map, the keyboard gets one memory location, 24,576. And what this location contains is a numerical value that corresponds to the key press. On a physical level, the way you can imagine this being implemented is to think about somebody engineering a keyboard where each key is a switch that closes a circuit when it's depressed. When that switch closes a circuit, a specific pattern of bits becomes what the circuit outputs. So if none of them are being pushed, it just outputs all zeros. Depending on which key you push, some of those zeros become ones. And which of those zeros becomes ones is all about how the keys are encoded and physically wired together on the hardware level. Okay. So coming back here. So let's say we want to read the keyboard. So what we're going to want to do is read it in the context of a loop. Almost all keyboard reading needs to happen in the context of a loop because when we look at a memory location to find out what key is being pressed, it'll tell you what key is being pressed right at that minute fraction of a second. So if we meaningfully want to read the keyboard, we typically need a loop that's just constantly looking at it to see what's going on. So we're going to write that. So I'm going to set up a symbol, a label, loop. And so I'll say, oh, actually, even before that, I'm never going to change my address register. So I'm just going to say beforehand at 24,576. I think there's a built-in symbol. I think you can just say at KBD, so you don't have to memorize that. Say D equals M. And then, oh, actually, we do have to, yeah, we're going to be using the address register to jump with. So we will need to do that. So now I'm going to say at loop. And so now I want to do an unconditional jump. So I'll just tell the ALU, emit a 0, and then just jump. And so this is a typical idiom for doing an unconditional jump in this particular machine language. So here's a basic keyboard reading program. You're going to look at it and say that does absolutely nothing because it reads the keyboard and then doesn't do anything. And you'll be right. But what we're going to get out of this is when using the emulator, we can monitor the value stored in D to see what kinds of numbers we get with different key presses. Now, the book has a table of all of these, of course, but I think there's a lot to be said for just getting down in there and seeing what the actual hardware does, and this is an attitude, especially if you're ever working on an embedded system, which is hugely profitable, right? You can read documentation all day, but if the hardware disagrees with the documentation, guess who wins? Yeah, the hardware. Reality always wins. Funny how that works. So I'm going to call this key1.asm. We're going to load this into our emulator. So single stepping through this is pointless. We really just need it to run. So what I'm going to tell it is I don't really want an animation. I just want it to run. So I'm going to hit this little fast forwardy thing. I'm going to press this. Really, you should be running. Okay, me and the emulator are not on speaking terms at the moment. Oh, actually, no, it's working fine. Let me fix how I'm handling this. Data flow. Fast. So here we go. You can see in RAM that's a 32 when I hit the space bar. You can see in RAM it's an 89 when I hit Y. When I hit J, it's a 74, and so forth. 84 when I hit a T, 82 for an R. Here's something kind of fun. So if an R is an 82, Shift R is also an 82. Yeah. In like a real physical keyboard, shifting and so forth gets taken into account. This one is just keeping things simple. Yeah, innocent. Yeah. Keyboards are wired to produce what are called ASCII values. I'll talk about what that means in a moment. So capital A is 65. Yeah, shifting an A still produces a 65. So the program is having trouble keeping up with my keyboard, and so D is constantly out of date. But having seen what these values look like, we can now write something a little more interesting. So we're going to put together what we've seen about the screen and the keyboard into a program that, for lack of a better phrase, responds to stimuli. So it'll be based on some loop that's continuously going. And what we're going to have it do in the context of this loop is the following. We're going to read the keyboard, put that into the D register. And now we're going to pick one of two dashes to print based on which key came in. So this is going to require doing some logic, right? We're going to have to get this to think about how we do a comparison so that we can actually make a decision. So let's think about this notion of comparison a little bit. It's pretty common to have lines like this in code. If A is less than 5, then you're going to do something. We're going to focus on this. You all noticed, right, that the ALU can tell us if the result of a calculation is negative, 0, or positive. What the ALU doesn't seem to contain is anything like less than or greater than or what have you. But here's the key insight. Any such expression can be rewritten as follows. That is, if you can get the right-hand side to 0, now you've got something where what the ALU spits out is meaningful. And if you're directly comparing two values, the way we get to that point is through subtraction. So if you set up a subtraction in your ALU, that's a means of doing a comparison. So here's what we're going to do. Let's say we want to do one thing if it's the letter A and something else if it's any other key. So A is a 65. And then we'll say D equals D minus A. So what we've done is we have set up a calculation in the ALU that can set the 0 and NG flags. And once those flags are set, we're in the position to perform a jump. We sadly can't do the jump immediately because we only have the one address register. So let's go ahead and, set up the jump we're going to need. So I'm going to call this first label -1. And so then I'm going to say, look at the value in D and jump if the result of my subtraction was equal to 0. So I subtracted, and now I'm saying jump if that's the case. So I'm not really going to have this as a branch target, but just for convenience, I'm going to have a line where I say -2. So for -2, I'm going to say at 20,000, and then I will say m equals 0, m equals not m. And then I will say at loop 0 semicolon JMP. Now I've got -1. I'll say at 18,000, m equals 0, m equals not m, at loop 0 semicolon JMP. So you might be thinking, good grief. Assembly language programs get long really, really fast. I would say, yeah, they do. Furthermore, instinctually, you're looking at this and thinking, look at all that replicated code. Why don't we refactor it? So the problem is, if we refactor it, we're overdoing what we can handle on the A register. So there's not actually a good way to refactor it. So yeah, you wind up with a fair bit of code replication, at least on this machine. There are some assembly languages where it's a little easier, but not so much this one. Yeah, Innocent.
Do you have a concept of a functioning?
Nope. Nope. There's moving values and there's jumps. And that's it. Yeah.
What if you had like a block of code that has some same elements and you jump them if you want to use them?
So the trick is that you've only got these two registers and you want to preserve those values.
Create a variable for them and store them somewhere locally and sort of read it from there if you want to. Unless if you don't have a concept of variable.
Oh, so maybe you could do that. Let's see if that would work. So well, actually, we're going to run this program, then we'll come back and see if your refactoring will work. So let's call this key2.asm. And let's try it out. I think you've got an interesting idea there, Innocent. So we'll come back to that in a moment. All right. So let's just run it. Of course, it keeps popping up a dash because I didn't type anything, and anything is not A. So it's arguably a bug. We actually want a keystroke. So we'll come back to that in a moment. So now if I hit A, I get that other dash. Of course, once I've hit A, it really doesn't matter what happens because there's nothing in the program that ever erases a dash. So yeah, so there are all kinds of problems with this program, but it's still pretty momentous. This is our first program that responded to a stimulus, in a noticeable way. So let's go through it and see if we can fix up some of these problems. So Innocent had an interesting suggestion. Why don't we just pick an arbitrary memory location, which is the place that we're storing on the screen, and then we can just drop into that stuff. Well, that's a neat idea. So let's do that. So at -2, what we'll do is say something like this. D equals A. So we're taking that location we want to use. And then we'll say at var for variable. We can think of a better variable name later, but we'll go with at var for now. Whoops. M equals D. No, I don't want D minus A. I just want D. And then we'll say at dash 0 semicolon JMP. And then we're going to have -1, where we say at 18,000, D equals A, at var, M equals D. And then we'll have dash over here, where we say, oops, at var, A equals M. And M equals 0. M equals not M at loop 0 semicolon JM. All right. There we go. So let's review this program thus far. This is not improving the functionality of what we had, but it's an attempt to address the code replication. So we'll see where we got. So we read the keyboard, we stash it in D, we subtract 65 from it, and then if it's equal to that, we jump to -1. So if it's not equal, we go in here to -2. We stuff a 20,000 in the D register, and we put that in our variable. Then we jump to dash. Now if it's -1, we have 18,000, and we stuff that into our variable, and then we just fall through to dash. In dash, we grab we point A at our variable, and then we set A to be the value at the variable. In other words, the value at the variable was itself a memory address, so we let A equal that M. Then we zero it out, we negate it, and we get our dash, and then we jump back and start all over again. So this was your idea, Innocent, right?
Yeah.
Well, in this case, it did make it longer. And the reason it made it longer is that it took us 4 lines of code to put something in a variable. And we were only really using 3 lines to begin with. But there's real value in the principle, right? You could imagine code replication far greater than this, and this is an effective solution. So we're going to do a save as. We'll call this key 3. And we're going to go ahead and load it in and make sure it works the same way. So key 2 was 16 lines. So yeah, we went from 16 to 21 lines. So it goes. And we're going to run it, and there's that dash there. But when I hit A, there's that other dash. So we have 2 bugs in this program. It prints a dash if there's no key press, and it never erases the dashes. So what's that?
Oh gosh.
Oh gosh, yeah. So we're going to start by fixing the first bug, that it's not actually waiting for a key press. So here's how we can fix that. We point the A register to the keyboard. We load the keyboard value into the D register. Now we just say at loop D semicolon JEQ. So what's the idea here? We read in the keyboard value to the D register. Then we say, if I got a 0, I'm just looping right back around. And so that makes it wait. You might be wondering, gee, a machine language program is this just big, long string of nearly meaningless instructions. Can we put in a blank line or something? And the answer is yes. Yes, absolutely. So I'm going to put a blank line here to kind of denote, here's a loop. And yeah, feel free to write comments like crazy in assembly language programs. I'm actually not usually a big fan of comments, but assembly language, yeah. So, well, I'm not going to worry about it for now, but just mentioning it some. So now we compare to letter A. And if it is, we go to -1. Otherwise, we go to -2. And then we do the thing. Okay. So let's do a save as here. So this will be key 4 as this program continues to evolve. And we're going to load this into our emulator. And let's go ahead and run it. Oh, I hit an A and I got my A dash. Now I hit a B and I got the other dash. So sweet, yeah. So now it's actually waiting for a key press before it does anything. You absolutely have to do that in every keyboard bearing program. Well, no. There might be the case that you want the program to be doing some things, and then if a keystroke happens to arrive, then you do something else. And part of the beauty of all of this is that nothing's stopping you from putting it together that way. It's just that having this cute little loop here is a way of simulating how we typically think about keyboard input. But we're not really limited to that. So the other issue was actually clearing what was already in place, right? So let's think about some ways that we might do that. So just conceptually, when should a clear happen? What do you all think? When should something get cleared? Spencer.
When the key is released, maybe?
When the key is released? Sure. We could do that. So let's think about how we might add that in. So right now, when the dash is printed, we immediately just jump back to that original waiting loop. So what we might do here instead is have it wait until it is a 0. And once it is a 0, we clear the location. So let's set up a label, wait for 0. I think we can do underscores. So let's work on wait for 0. So what we're going to say is at KBD, D equals M, D semicolon, at wait for 0, D semicolon, JNE. So we're using the not equal to feature of the jump. Say as long as it's not a 0, we're going to keep doing wait for 0. So now that it's come out, we know that it's equal to 0. So what we do is we say at var, so we're getting our screen location. A equals M, M equals 0. And then we say at loop 0 JMP. Yes?
zero means nothing.
Oh, yeah, so let's review that. Every location in screen memory corresponds to 16 pixels. Each bit in the pixel each bit in the memory location is one of 16 pixels. So what we've been doing is setting all 16 bits at a memory location to 1, and so then it displays a dash. Now what we're doing is setting all of those bits to 0, which erases the dash. So let's try this out. I didn't do a save as, so this is still going to be key 4. We'll reload it. And now it'll run. So when I hit an A, my dash is there as long as I'm holding it down. The instant I lift it, bam, it's gone. If I hit any other key, as long as I'm holding it, the dash is there. The instant I lift it, bam, it's gone. A, not A, A, not A, not A, not A. Yeah, not A, A. Yeah, Andre.
Why is it only A in one location?
Because I was lazy. So specifically, right? So let's review the program and see why that's the case, because it's a great question. What I do over here is I load a 65 into the address register and compare the data register to that by subtracting. 65 just happens to be A. So when I subtract, if it's an A, it jumps to -1, which says, put it at 18,000. If it's not A, it just falls through here. And it puts it at 20,000. Yes, Spencer.
So if we want to implement any of these like keys specifically, we'll have to like experiment and find out what the number is, and there's no like method of knowing.
The main method of knowing is looking it up in a giant table.
Okay.
Yeah, I can tell you that, yeah, A is 65, and they go in ascending order upward from there. For the letters. For the numbers, I think it starts at like 40 to 49. I don't remember for sure. I'll talk about what the encoding scheme is in just a moment. But it's a good question. Yes?
So this looks very cool. So sorry.
No worries.
If I want to take input from, let's say, a camera,
Mm-hmm.
like, does it still follow the same like procedure here? There is probably a number representation of an input from a camera.
Absolutely.
Okay, some of that.
Right. So yeah, let's think about that for a moment. If you're writing a machine language program to interact with a camera, the camera needs to be set up so that each image coming in just winds up occupying some large section of memory. That's precisely how one reads from a camera. In fact, is there's some means by which a specific region of memory is allocated for the images coming in, and that's called a frame buffer. And from there, you just look at the numbers. Yeah. So obviously at the machine language level, that's how it works. But it's also how it works in a higher level language. So if I'm writing a device driver for a camera in a language like Java, for instance, what I need to get from the driver is the location of an array that contains the data from the camera. So the frame buffer in a high level language is just represented as an array. And then I've got everything I need. As you would guess, I'm speaking from experience. Oh, I have absolutely done this. Yeah. Yeah, Andre.
How would we go about, like, so we have like 20,000 in the A register, how do we go about like incrementing by like a certain value so we don't always,
So you don't have to go in these blocks of 16.
yeah.
So that's tricky. Let's see. obviously there is a way to do this. You won't technically need to do this for this assignment, but it's an excellent question, and I'm going to walk through conceptually how you go about it. So Andre is pointing out we don't always want to do our screen display in blocks of 16. So how could we think about doing it in blocks of something other than that? You know, how do we do it at the level of one element at a time? So let's walk through it conceptually. To actually implement this in machine language sounds really painful, but let's see where we get. So we would have two variables, right? One of the variable is like the screen memory. Then we have another variable, which is going to be an offset into that screen memory. So you could, in principle, do this with just one variable. And here's what that would look like. You do just one variable. Let's say we call the variable pixel. We would then use division to figure out the screen memory location. So you take pixel, you divide it by 16, which is the number of pixels per memory location. Then you add it to, you know, some base value, in this case 16,384. And then for the offset, you take your pixel mod 16. And that tells you which bit you're working on within it. What's nice about this setup is that you could have a single variable tracking where you are as you're incrementing, which is really nice. The downside is you need to divide and use mod, which in machine language is a pretty big downside. So if I were coding this directly in machine language, I would actually use two variables. One to be tracking what memory location I'm at, and one to be tracking my offset. Every time I increment my offset, if I hit 16, I reset it to 0 and increment my screen memory. And if I'm writing machine language, that is fundamentally easier to do than to come up with my own personal implementation of mod or division. Everybody with me so far? Yeah.
I mean, so this idea of like modding and dividing is usually applied if you're using a two-dimensional array of some sort, and you wanna find like a row or column of something. Right. How is it like useful in this case? Maybe I kind of don't understand exactly what we mean by pixel.
Well, that's a great question, Innocent. And a big part of the answer is to say that thinking of screen RAM as a two-dimensional array is really good conceptually. That's really what it is effectively a two-dimensional array. So the outer dimension of the array is the memory location. The inner dimension of the array is the position within that memory location of that pixel. Those are a really good connection because they're really, from a data structure point of view, the same thing. Yeah.
So is a pixel like a one integer value? Let's say 255.
A pixel is just a 1 or a 0. Because this is a strictly black and white machine. In other words, a pixel is either on or off. And so if it's on, it's black. If it's off, it's white. Is the way it's set up. Yeah. All right. So yes, we've got screen memory and we've got an offset. So let's say on a pixel by pixel level, I want to be able to turn something on or off. To do this, we resort to a technique known as bit masking. So you're probably thinking, well, at some point we clearly do have to code this. And the answer is yes, in chapter 12, you'll actually be coding this, but not in machine language. But I think it's really handy to know what the underlying concept is to anticipate what we'll ultimately be doing. And to think about when they pack in data like this, how do you get at the stupid stuff? It's a very natural question. So here's how it works. Let's say I want to turn on bit 4. Okay? So what I can do is I take the value at that location and I do an OR, where in my OR I have a 0 at bit 0, 1, 2, 3, and then I have a 1 at bit 4, and then I have zeros all the rest of the way through. So when I OR it with that, because 0 is identity, that leaves all those bits alone. But I ensure that bit 4 is now a 1 because a 1 overrides either a 0 or a 1. And so it's now been set. To clear with a bit mask, you use and it's totally the complement. Since 1 is the identity value for an and, you fill up with 1s, and then you set to a 0 just the bit that you're concerned about. So that's what's called bit masking, and it's a way to isolate a specific bit within a memory location in order to give it the value that you want. So if we thought we had an arrangement like this with the screen memory and the offset, what we would do is make sure that the offset value is used to construct this bit string. Of course, the next question is, how do you do that? So here's a really cool way to do that. Whoops. Still erasing. So how you do that is, so this value you're going to store, you set that value to 1, okay? And then let's make a copy of your offset. So you could say something like n equals the offset. Then while n is greater than 0, x equals x times 2. Or cheaply and effectively, x equals x plus x. Now, if you're thinking about how you would do this in machine language and you don't have a multiply routine, you can just add it to itself. Oh, and very importantly, n equals n minus 1. Yeah. And then you just loop through, and now you've constructed the appropriate bit value. If you're going to do an and, then after all of this is over, then you'll say something like x equals not x. And that'll get you the mask for the and. And yeah, that's how you do it. Now think about how straightforward it was for me to throw up a while loop to do this compared to setting up the jumps and my 2 registers. Again, this is a pretty primitive machine language. Almost any actual commercial CPU you'd use has a nicer machine language than this. The number one form of nicer that matters is more dang registers. You know, use an Intel CPU or whatever, you're gonna have at least 64 registers sitting on that thing, which is great because for every register you have, that's a location in memory you don't need for variable. At least the variable's an integer. If it's anything else, well, you're probably going to need to go to RAM. But for integers, it's great. For integers, it's great. And as you can see, even to set up something like a while loop or whatever, you need a lot of integers running around. Cool. Other questions so far? But yeah, you all can see why bit masking is maybe out of scope for this assignment. So ultimately, in chapter 12, you will be writing operating system code that will be directly pixel addressable. In other words, there's going to be an operating system API that lets the user say, I want to turn this pixel on or this pixel off. And to do that, yeah, you're going to have to code all this, but you'll get to code it in a high-level language, which will then get compiled down to machine language. Because, yeah, life's just too short. Or something like this. Cool. Other questions thus far? Yeah, Brandon.
So with our key pass right now, if you, for example, hold A and then hold another key, will that apply both dashes or does it get rid of one?
Let's find out. So A is that one, B is that one. I'm holding A. Actually, before I push down B, I want you all to guess what you think. Yes. What do you think? Yeah, Andre.
Just one, because you can only have one.
Okay. It's just one. Yeah, Andrew.
Pressing down A, wouldn't be going through that loop at the very end of our code that's just like waiting for it to turn to 0. So like maybe like once you press B, it won't change to 0 yet.
That's a pretty interesting theory.
So
Yeah.
I guess
I'm going to push B right now. So here's what happened. So I pushed down A. Now I push down B. And I'm actually still holding A. But when I lift B, it counts it as a key raised and puts a 0 in the keyboard. So Andrew is pretty insightful here. But the way that the emulator works is also pretty critical. So let's kind of walk through it and make sense of all of this. So, oops, got to be magnetized. I was going to point with this thing and this thing, like, ah, what's going on? All right. So I'm waiting. I push an A. I jump to -1. I load that up. I fall into dash. I've printed my dash right here. Now I'm in wait for 0. I'm still holding down A. If I push down on B, I still didn't get a 0. So this loop keeps going. I'm still holding down A, but when I release B, the emulator counts that as a key raise and puts in a 0. Now that it's a 0, it falls through. It erases the dash and comes back up here. Because I lifted up the key, of course, now it's going to wait until I actually push something before it displays anything. But I really love this question, Brandon, because it gets at the fact that when you're writing machine language code, there is literally nothing between you and the machine. That is, every last thing the machine does, you are directly controlling. There's no compiler between you and the machine. At this point, there isn't even an operating system between us and the machine. It's just us and the machine, and at that point, you can literally know everything it does. Most of the time, this is power we don't necessarily want because it has a huge burden, right? Oh man, I know exactly what it's doing. There's no operating system getting in the way. Oh, there's no operating system providing anything at all. That's kind of a pain, right? Yeah, but This is pretty cool, right? Because where this really counts in a modern context, more often than not, is going to be in what's called an embedded system. So why would it matter in an embedded system? So what I mean by an embedded system, I mean, you've got some microprocessor hooked up to some circuit board and directly controlling some hardware via the circuit board. Here's the kicker about these things. The economics of manufacturing tends to demand as low a price as possible for the CPU component, right? The cheaper you can make it, the better. The less memory it has, the better. And if the calculations it's performing are straightforward, well, maybe you don't need something that has, an operating system. Instead, you can just directly write code that talks to the hardware. Ultimately, an operating system is just a giant program that lets us talk to the hardware in an abstract way. And so in my operating systems class, of course, we look at modern operating systems and everything that they provide. But fundamentally, they're not actually necessary, right? You can always just talk to the hardware. In machine language, you can do that. The language we use in the operating systems class is called Rust. And it's a rare high-level language in which you can do this is what's called coding to the bare metal. No operating system in between. So Rust is actually a high-level language in which you can code to the bare metal. In practice, if I'm doing embedded coding and I'm coding to the bare metal, I'm probably going to program in Rust rather than go straight to machine language. But, it's nice to have machine language there. The one time I wrote an embedded driver in machine language was during my first year of graduate school. We were building a robot, and we obtained some servos to control the pan tilt of a camera that was on board the robot. And so I actually wrote a bare metal machine language program that received inputs over the input port to the CPU. And that input was just saying, this is the angle at which I want the servo to be pointing. So that came in as an input. And then I wrote a machine language program that took that value and figured out what electrical pulses to send to the servo motor to correspond to that position. And the way I figured out those electrical impulses to correspond to that position was experiment. So I had one of these servos set up with a toothpick super glued to it and mounted on a board with, I am not kidding, a protractor. And I experimentally determined for each level of resolution of angle that we wanted, what electrical pulses to emit to get that angle. That was cool. Yeah, it was a lot of fun. I really, really enjoyed doing that. It took me weeks. So then, yeah, my program wound up just having kind of a giant lookup table saying, as these angle values come in, here are the values of the electrical impulses to apply to the wires of the servo. And yeah, I coded all that with no operating system, no high-level language, just me and the metal. You can probably glean from the fact that I've had that experience and some similar experiences why I really love teaching classes like this. I love this stuff. Do I want to code in machine language every day? No. And you're not going to do an awful lot. So this is it for programming machine languages. These two programs you're writing for this assignment. But you're going to learn a lot by doing it. Yeah.
So you just say that with this kind of programming, we can literally talk to the hardware immediately.
Yep.
imagine that maybe one day I want to screw up my laptop very, very badly.
Okay, yes.
Sort of write a very bad code that can probably overflow the RAM or sort of
Yep.
wipe out the whole
Yeah.
like hard drive. Is it possible? Like, can I write like an assembly program that says go and delete everything in my hard drive?
Yes.
And how would that work?
Well, the answer is a qualified yes. One of the major services provided by a modern operating system is security. And security isn't just about stopping bad guys, it's also about stopping errors. So in a modern operating system, if you start up a program, it actually puts the program in what you might think of as a sandbox. That is, it sticks that program in a region of make-believe RAM, or virtual memory, as it's called. And there's actually hardware support for all of this that the operating system interacts with. Again, this is more of a topic for my operating systems course. But in the virtual memory, all memory accesses it does get translated by the operating system into memory locations that are in the region that the operating system has set aside for that program. So the program doesn't even have a way of getting outside its sandbox, because any memory location it talks about is stuck in the sandbox. Of course, there's always a way around things, right? And so what it really comes down to is one kind of way around this is if you can trick the operating system, then there are ways to try to get a polluted value into what's called the operating system kernel, which is running below virtual memory and doing all of this stuff. On an older machine before virtual memory, yeah, you could absolutely positively hose it. And there are many forms of doing that. For instance, the network drivers run in the operating system kernel. Okay? So it turns out that many operating systems had a subtle bug in their network drivers that if you overflowed the input buffer for the driver, in other words, the driver is expecting X number of bytes, right? Well, there are some tricky things one could do to send a message that was bigger than that would then overflow the buffer and begin overwriting actual code that's laid out in memory after the buffer. So to do this hack, took a lot of work. So one thing that's become really, and this is what's called a buffer overflow attack. So buffer overflow attacks exploit weaknesses in the C programming language in which most operating systems are written. Something that's really bad about C is that it doesn't do any bounds checking on arrays. So in C, an array lookup is simply a memory access that's completely unchecked. So that's bad. Yeah, and so a lot of operating system security holes are based on finding exploits like this. So what's cool about a language like Rust is that it's got all the low-level access of C, but it's got all of this access protection that keeps such bugs from happening. But yeah, it's a great question. Cool. So just to recapitulate, your two programs to work on this week are a program that multiplies two numbers. So I think the two numbers are going to be sitting there waiting for you at like memory location 0 and 1. And then you write a loop that multiplies them. Conceptually, it's just repeated addition. Take one of the factors, use it as a loop countdown. The other factor can be the accumulated product. So every time you decrease one factor by 1, you add the other one back onto itself and kind of build it up from there. So conceptually speaking, it looks something like this. If I want to multiply 2 times 3, then I set up one variable to be my product and another to be a counter. And so my counter is initially 2 and my product is 0. So each time through, say my counter is greater than 0. Awesome. I add 3 to my product and I decrement my counter by 1. Counter is greater than 0. I add 3 to my product. And it turns out 2 times 3 is 6. Algorithmically, that's how you're going to multiply. The other program you're going to write is, as long as any key is being pressed, it should fill the screen. If a key is released, it should be wiping the screen. So what you're going to do is you're going to have a variable tracking which screen location you're currently updating. And the loop's just going to go forever. So the loop is going to be constantly advancing through every location in screen memory. And when it gets to the end of screen memory, it just wraps back around to the start. Then if a key is down, you put all ones in it, if any key is down. And if no key is down, you put all zeros in it. And that's the algorithm for that. Yeah, Andre.
For the multiplying part,
Yeah.
does it really matter if like one of the two numbers that, or one of the numbers that decrementing becomes 0 rather than keeping its original value?
Oh, you want to kind of make separate variables to store them. Yeah, that's what I'd recommend is have a counter and a product, copy the values over, and then just leave them alone in RAM. Yeah, Andrew.
So after we like write this program and like kind of finish it, does it matter like what it does after it's done with the loop?
It's a great question. The convention is just stick an infinite loop at the end of the program where that always jumps back to itself. And so what's nice about that is you can tell it to run without animating, and then the final value will just be sitting there in memory, and it's easy to see even while the program is constantly jumping back to itself. Whereas otherwise, the program kind of just charges all the way down through memory, and it's like, what's going on? You know, no real program, so to speak, does that, but for these purposes, that's a nice way to handle it.
You show, I'm looking back to the program again, to show dash and show middle, right? Maybe scrub, yeah, I want to let it sink in.
Well, I'll post these programs on Moodle.
Oh,
Yeah, so you don't have to totally transcribe them. I'll pack them up and post them this morning. That should save you some trouble. All right, happy machine language programming, and I'll see you all on Tuesday, whereupon we will begin working on engineering a CPU.